plan to cover. Yeah, so today we'll look at very generalized notion of impedance admittance in an LPTV network. And as usual, we'll start from an LTI network, which everyone is familiar. Say this is a linear time invariant network. I'm interested in finding the impedance looking into this port at a frequency f. Okay, so that at a frequency f. So how do I find it? Right. So this basically, this is voltage by current at the same frequency. So you have to apply a current source at a frequency f. So let's say this is e power j 2 pi ft. And then I'll find what is the voltage of t. And if the impedance for this is that of j 2 pi f, the voltage will be the impedance times, I of t is e power j 2 pi f. And please remember, I am writing in time domain because this is a complex exponential. Okay? Complex exponential is an eigenfunction for linear networks. So you apply e power j 2 pi ft, the time domain response will be scaled version of the same complex exponential. Okay. So now let's say I am interested in finding the admittance at the same frequency. What do? It is basically I by V. So I'll have to apply a voltage source. So now I'll apply a voltage source Ft and measure what is the current, right? And if the admittance is y of j 2 pi f, the current will be this times e power j 2 pi ft. So basically you apply a current for finding the impedance, you apply a current, find the voltage, take the ratio, that will give the impedance. For finding admittance, you apply the voltage, measure the current, take the ratio, that's going to give the admittance. So now let's say I take this. We'll come to that actually. Hold on. I understand. You are saying to find impedance, why can't I apply a voltage source? Strictly speaking, you can't do that because the definition of impedance is voltage by current. So the input is current. You measure the response of the LTI system to this input current, and the response you have to measure is voltage. Okay. So this is the admittance measurement experiment. So here, let us say instead of applying a voltage source, I replace this voltage source by a current source with the same value. Okay. So what I am doing is, earlier I applied a voltage e power j 2 pi ft, measured the current. So now I am replacing this voltage source, applying a current source with that same value that I measured earlier. Clear? So now can you comment on what this voltage will be? If I of t is this, sorry, no, this is the current. Okay, this is, see, the experiment I did was I applied a voltage e power j 2 pi ft, measured the current I got. Now I am, the same current that I measured, I am applying as the input. I am trying to measure what is the voltage. No, forget about what is it. It is the same. Why is that so? Substitution theorem. Everyone is aware? Right? Simply says if you have any network, any element, you find the voltage across it, and if you know the current through it, I can replace it by either a current source of that value or a voltage source of that value, and nothing else will change. And by the way, so The substitution theorem, do you think it is valid for any network or only for linear network? Any network? Only linear network? No one is supporting linear networks. Yeah, why? Yeah, I mean that's yeah, but okay.
There is an ambiguity when you have a current controlled voltage source or controlled current source. There is an ambiguity when you remove. Otherwise, it is at least with the derivation it is not coming. So
it's actually doesn't require anything, right? Because so I mean, let's say you take any network. This can be anything. I put dinosaurs, transformers, anything inside. I take some element. Okay, I see that the voltage across it is some V and current is I. So let us say I apply two current sources like this. Sorry, current sources like this. Did the network change? No. Basically, I added a 0 ohms current, right? So the voltage will still be V. So voltage here is still V. This is still V. Okay. So now can you tell me what is the current that is flowing here in this wire? 0. I mean this incoming current is I. Same I goes here. So 0 current flows in these two wires. So if 0 current flows, what can I do? Oh, it's an open circuit basically. There is no need to put it here. Right? So basically this is the same. That's all.
If there was a voltage current source inside that block, and that was supplying a current to a load, let's say resistor.
We can discuss it later. I'll because we are digressing a lot. We'll come to that later at the end. Okay. So yeah, let's come back to this. So yeah, this is at least clear. So if I apply a current I of t, which is the same value that I had measured earlier, the voltage is e power j 2 pi of t. Now if I scale the current and say I am applying a current of e power j 2 pi of t. Earlier it was y times e power j, and scaling the current by the factor y. So it's a linear network. This will also come, right? So now it says that if I apply a current I, which is e power j 2 pi of t, I have this voltage. And in the first experiment, we did the same thing. I applied a current e power j 2 pi of t, and this was the voltage. So what can you infer? Yeah, z of j 2 pi f is. I mean, this might look trivial, but let me come to the next part. So for LTI networks, you can interchange. That's the point. If you find the impedance, you apply a voltage source, measure the current, and take the inverse. That works. No problem. Now the fun starts when you start to deal with LPTV networks. So let's say this is an LPTV network running at Fs, and in general, in most of the practical circuits you encounter, the time variance will be due to the fact that you have a time varying resistance or a conductance, and mostly the capacitors, inductors, they will all be constant. Generally, most of them. But anyway, so let's say you take any LPTV network here, I try to do the same thing. So first I apply a current and try to measure the impedance. So I am interested in finding the impedance at a frequency f. That's basically voltage by current at f. I have applied a current e power j 2 pi f t. We know that this is a periodically time varying network. So the impedance is also periodically time varying, right? So what will be my, if my input current is e power j 2 pi ft, output voltage will be what? This times e power j 2 pi ft. Now again, you know, this is a periodic signal in T, so I decompose as Fourier series. So I'll have zk of, I mean, this is similar to the harmonic transfer functions, right? That's all. So I'll have e power j 2 pi f plus k wisdom, right? It shouldn't be surprising. You apply a tone at f to measure the voltage, you see it has all frequencies at f plus k wisdom. Great. But let us say I'm interested in the impedance at f. That is the strength of the voltage at f divided by the strength of the current at f. What is it? Z0, right? Is it clear? Right? Now we can do the same thing for admittance also. Probably have to copy paste it. So here I'll have to change the excitation to voltage and measure the current, and here things get flipped. Y is I by V. This will be the current. Yeah. And similarly the admittance at f is Y0. Same thing. So now let's try to do the same thing as we did for the LTI case and replace this voltage source by the equivalent current source. Okay. So now I know that this is the current, right? Okay. So I'll probably split it like this. I'll say y0 of j2 pi f e power j2 pi ft plus all the other terms, right? So now instead of this voltage source, if I apply a current source of this value, right, which contains all frequencies of the form f plus kfs, then what will be the voltage? If I apply a current of this form, then I know my voltage is 2 pi ft, right? So if I look at the strength of the voltage at f, that is same. You just have e power j 2 pi ft. Okay. So now I'll do the same thing. I'll scale the current. So instead of applying y0 times e power j 2 pi ft, I will say I apply something like this. Oops. Is that fine? So the voltage will also scale. Okay. Now the point to note is, only if I apply a current which has all these frequency components, right, f plus fs, everything, only then my voltage will be exactly this, right? And this should not be uncommon, because we have frequency translations in the LPTV network, and all of these frequency components are aliasing back so that we get only e power j 2 pi ft. So now let us say I say my current is only e power j 2 pi ft. Then I can clearly say I will not get the same voltage as I got here. Right? Only if I apply a current at all these frequencies, my voltage will be this. Clear? But now what I am saying is I am not applying these terms. I am applying only e power j 2 pi ft. It makes sense that voltage at f need not be equal to this. Fine. But in the earlier experiment, we had applied a current e power j 2 pi ft, and we found that the voltage at f was basically z0 times e power j 2 pi ft, right? But we know that if you do this experiment, we already saw voltage at f is z0 of j 2 pi f times this. Is that fine? So from this, what can you say? They need not be equal, right? Z0 and Y0 need not be equal. Or need not be equal to inverses of each other. Is that fine? So this is the major distinction between LTA and LPTV network. So here you will have to be careful. For finding the impedance, you need to apply a current source and measure the voltage. You can't simply flip around if you are interested in finding Z0 and Y0. Okay? But fundamentally speaking, you know that the conductance is inverse of resistance and the impedance is inverse of admittance, right? And here we have a time varying impedance and admittances. So this will still be valid. Yeah, if you find the impedance as a function of time, they will be inverses. But what we yeah, I mean, if you correct, if you exactly, I mean, basically this is true, but Z0 yeah, I mean, basically this is what we just proved, right? This just says the DC term of this and DC term of this. Just because these two are inverses of each other doesn't mean their DC components will be inverse of each other. That's all. And I mean, this is all happening because we have been sticking to the LTI notion of impedance, where we are just looking at the current and voltage at the same frequency. But in LPTV, we know we don't only have a frequency at f. What all the frequency components we have? Yeah, f plus kfs. Okay. So we'll now see a more generalized form of an impedance, where you take the currents and voltages at each of these frequencies and take into account the frequency translations. And in principle, you will have to vary k from minus infinity to plus infinity. But in practice, let us say you find that beyond some minus k0 and plus k0, the harmonic strengths are negligible. You can restrict our k to this. Okay? So we'll basically try to find the relation between voltages and currents at all these frequencies. And how many frequencies are there? 2 k0 plus 1. Okay. F minus k0, F plus k0. Okay. So yeah, let's quickly do that. And we'll start with the time varying conductance for simplicity. Okay. By definition, I know I of t is g of t times v of t. Now, for the LTI case, we are only applying a voltage or a current at f. But now we will try to apply voltage at all these frequencies. Okay. So the voltage is basically summation k going from minus k0 to plus k0. Somebody say. I mean, we need to, I mean, to be exact, we have to take from minus infinity to plus infinity. But real life, we assume that beyond some harmonics, the strengths are negligible and we restrict ourselves. So this is, okay. Instead of applying one complex exponential, I have applied 2k plus 1 complex exponentials at these frequencies. Now I know g of t is also a periodic signal. It's a periodically time varying conductance. So I will decompose it as its Fourier series. Now, I mean, a more convenient way to represent this, how do you represent it conveniently? A more compact form to, I mean, basically this, huh? Yeah, I mean, but, okay, I was getting it representing in terms of a matrix. See, basically what it says here, we are trying to relate the voltages and currents at multiple frequencies. So, I will say this is minus Vk naught plus 1. So, 0. So basically first row relates, I mean this gives the strength of frequency at f minus k naught fs. This gives strength at f minus k naught fs plus fs. This is at f plus k naught fs. So similarly I'll try to find the strength of the currents at these frequencies. So k naught. So what is the size of this vector? It's 2 k naught plus 1 cross 1. So what should come here? I mean, you know, both of them are column vectors, this dimension. So if I have to relate them, what should come? Yeah, we should get a square matrix, right? So, and let's quickly write few of the entries to understand how we will do that. Let's say we are interested in the first term here. This first term multiplies V minus k naught, and I mean before that the first row, here we are interested in finding the strength of the current at what frequency? I minus k naught, the strength of the current at what frequency? Write in a different color. This is f minus k naught fs. Okay. So we have V minus k naught, which is voltage at f minus k naught fs. So here basically k is minus k naught, right? So this is multiplying with one of the terms here to generate a current at this frequency. It should be G0, right? Because voltage is already at the same frequency, so 0. So what will be the second term? Think carefully. Second term, here voltage is at f minus k naught fs plus fs. We are still interested in the current at f minus k naught fs. So this will be G minus 1, and yeah, doesn't need an expert to fill the rest. This will be what? Last term will be what? We have f plus k naught fs. I need to relate it to f minus k naught fs minus 2 k naught. What will be the this fellow? So here, let me write it here maybe. This is I minus k naught plus 1. So now I am interested in a frequency of this form. That is, I am interested in a current at this frequency. This we apply by multiplying these two rows. So the first term multiplies with this. Voltage is at f minus k naught fs. What should, this is basically plus 1. So what should multiply this voltage to give a current at this? Sorry, this is the voltage. This multiplies this and gives this. G1. So next will be obviously G0 and so on, right? And similarly it will keep increasing down. And the last will be, what will be the last entry? 2 k naught, right? That's all. And the last will be G0. So we will quickly copy this. Now here, if you notice, all this G0, G1, G2, they are all basically the Fourier coefficients of our periodically time varying conductance and real world, real conductance. So the Fourier series have conjugate symmetry. So G conjugate minus K is Gk, or G minus K is what? G conjugate of K. So I can replace this as G conjugate 1, this is G conjugate K1. And now if you look at this section of the matrix, they are just conjugates of each other. So what kind of matrix is this? It's a Hermitian matrix. I mean, basically the matrix conjugates transpose the same as the matrix. That's all. I mean, this makes your life simple because you don't have to find out all of these. You find out one half of the matrix, the other half is filled. Right? So now you can write I as some G times V. Now this you can write even for frequencies, right? Earlier we could write only in time domain like this. But now we have formed a matrix relation where you have related multiple frequencies, and this also takes into account the frequency translations. Right? And similarly you can start with V of t to be R of t times I of t, and you can find a resistance matrix like this. Okay? And what can you say about R and G from these two equations? Yeah, I mean, from here, what can you say about, I mean, here. In this equation, if I multiply R inverse on both sides, I'll have I, and this is basically same as G times V. So you simply compare and you can find, and this also follows our conventional, LTI notion that matrix, I mean, the conductance is inverse of the resistance.
So why do you say that G is a real quantity?
G, okay, G of t is real, right?
G of t is real.
That's all.
No, G of t is real because there can be capacitors.
No, this is a resistor, time varying conductance. By conductance, it just means a resistance. Right?
In general, only resistance.
Yeah. Let's also quickly look at capacitor, right? So, as I mentioned, capacitor is usually constant, okay, but still you can, represent in a matrix form like this, and I of t is, and okay, if the capacitor also varies with time, what will be the IV relation for the capacitor?
V of C by dt.
Same.
C dv by t plus dc by dt into V.
Right? I mean, because fundamental relation is this, you derive everything from this. Okay. Cool. So in our case, the capacitor is constant, and we'll do the same thing. We'll assume that the voltage has all these 2k plus 1 complex exponentials. So what is I of t? It's basically C times derivative of this. So what are the constant terms that will come after differentiation? Come on, let's finish quickly. I'm basically differentiating this with respect to time, right? That's all. Huh? I'll have J2 pi, and then within summation I'll have Vk F plus Kfs, same thing, right? So if I have to, represent it in a matrix form, here. Here let's say I have V minus K naught, V0 to V K naught, and on the RHS I find the strength of the current at the same frequencies, I minus K naught, I0, and K naught. So what will this be? I have constant J2 pi C that comes out. And first of all, this is a constant capacitor, it's not time varying. So if I apply a voltage at a frequency f, what are the frequency components I can get at the output? It's a constant capacitor. It doesn't vary with time. I apply a frequency f as the voltage or current, whatever. What will be the frequency? Okay, I is C dV by dt, right? I am saying capacitor is not changing, which means this is the relation. I apply a frequency f as voltage. What frequency components will be? Only f. So what can you comment about the matrix now? Now only, I mean, frequency at f minus k naught f is, yeah, only result in current at f minus k naught f is. It won't mix with any other terms. So it will only be diagonal, and you can find the diagonal to be the frequency component function. All others will be same. Okay, because only this will go with this, V0 will go with F, and so on. So even for capacitor, you can write it as J2 pi. F is a matrix now, diagonal matrix, times C times V. Okay. And in general also you can do for any impedance, I to be Y times V, and similarly voltage is Z times I, and you can find that, so Y is not a vector, so Y will be Z inverse. And usually these matrices are called the impedance or admittance conversion matrix. Okay. So, okay. Last thing I wanted to cover. Yeah, okay. So, just like how we related voltages and currents, if you take an LPTV system, we have input and output. You can also relate V out to be some H times V in. Okay. And probably I think we'll do that in the next class maybe. And okay, just one last thing. The takeaway from this class is the fact that you represent for LPTV network everything in terms of vectors and matrices, and you can follow the same thing that you might have learnt in LTA networks. For example, say you have a LPTV network like this, right? So let us say, I mean, this is a resistance. I mean, the entire thing now, you can think of it as a resistance that varies periodically with time. So I can find the conductance matrix for that. I'll say this is a G matrix. Similarly, I have a constant capacitor. I know the admittance matrix for the capacitor. Do it like this. And let us say you are interested in finding Hk of J2 pi f. What is the input you will apply? P power J2 pi ft. So if I were to write a V in vector that says the strength of the inputs at all these frequencies, how will it look like? My V in of t is what? P power J2 pi ft. If I try to form a vector which says the strength of the V in at all these frequencies, you will have zeros, right? So now this entire thing can be simplified like this, right? I have a source. This is a vector now. A G matrix. Right. Now I can find what is my everything you treat as matrices and vectors, right? That's all. So now you use KCL as usual. What is the current leaving this node? Yeah, I mean this is matrix, so be careful with the which product comes first. So this will be G times load minus V in plus this current which is basically y times V out 0. Right, now we can find what is V out, right? V out is basically G plus Y. This is V times G. So V out vector is basically G plus Y inverse times G. So, okay. This will directly give all the harmonic transfer functions you want, and again it depends on what the value of k naught you choose. And in fact, this is the basis of kind of analysis called harmonic balance. So some time back we discussed about periodic steady state simulations, where how we can find or analyze LPTV networks in cadence. And there is frequency domain based simulation which solves for LPTV networks, and that is called harmonic balance. And basically that does this. It finds the matrices, conductance, admittance matrix for the components in your network. Depending on the analysis you have chosen, it will form the Wien vector. And then it will assume that my V out is also a vector, say it's A minus K naught, A0 to A K naught. It will try to find the values of all these unknowns so that the strengths of the harmonics are balanced on both the sides. Because we have to solve this for each frequency, right? This is for F minus K naught Fs, this is for F. When you expand it, this matrix, V out will have similar entry. So each row corresponds to one particular frequency. So the tool will try to find out these coefficients so that this entire relation is satisfied. Okay. Yeah, let's stop.